Ever feel like you're just drowning in information? Articles, data, research papers. It's overwhelming. And all you really want is the key stuff, right? Reliable, quick, without your head exploding. Well, that's exactly why we do these deep dives. Today, we're looking at something genuinely fascinating: laser-induced breakdown spectroscopy. LIBES, for short. It sounds like science fiction, maybe, but it's radically changing how we find and recover critical minerals. We've gone through some really solid research for this one. Papers from Alvarez, Galli, Harman, Yanovsky, Mazood, and a great overview from Storm, all pretty recent. So our mission today: let's unpack how LIBS works, look at its, frankly, mind-blowing uses in mining and recycling, and figure out what it means for you and how we get the resources we need efficiently, sustainably. Okay, let's dive in. This LIBS technology, at its heart, what actually is it? How does the laser thing work?
Right. So LIBS, it's a type of spectrochemical analysis, basically using light to figure out what stuff is made of. It's built on atomic emission spectroscopy. The core idea is you make atoms glow, and then you read their light signature.
Make them glow how?
With a laser. A really high-energy pulsed laser focuses on a tiny spot on your sample. This creates a tiny puff of superheated material, a plasma. Just a minuscule amount of the sample gets vaporized.
Okay, a plasma. Then what?
Well, as that little plasma cloud cools down, it emits light. And here's the key part. Every single element gives off its own unique pattern of light, like a fingerprint. Specific colors, specific wavelengths.
Oh, okay.
So we collect that light with a spectrometer, analyze the pattern, and boom, we know exactly what elements are in the sample, and even how much.
And you mentioned it's practical.
Hugely practical. One of the biggest advantages, really, is that you can do this fast. On samples that haven't been treated or prepared, think about that no complex lab prep needed sometimes. You can get results almost immediately right there. That's the revolution.
Okay, that speed and lack of prep sounds impressive.
Yeah.
But let's put it in context. Why is this such a big deal compared to, the methods we've been using for years? How does LIBS really stack up?
Yeah, that's where it gets really interesting. In traditional methods, things like SEM-based automated mineralogy.
Using electron microscopes, right?
Exactly. They have some serious drawbacks. First, you need really carefully selected samples. Often you have to prepare these meticulously polished thin sections, super thin rock slices, and that means you can only scan a tiny area, maybe a few square centimeters. It limits your view.
And I bet that takes time.
A lot of time. And it's expensive, so you can only really analyze a few chosen samples. Plus, they're not great at detecting light elements. Think lithium really important now, but hard for those older methods.
So you end up with a picture that might not represent the whole rock formation.
Precisely. You get data at the centimeter scale, maybe, but a drill core represents meters of rock. It's a problem of representativeness.
Okay, so that's the old way. How does LIBS flip the script?
Well, first off, minimal sample prep, sometimes none at all. You can zap a drill core directly. Yeah, the first few laser shots often just clean the surface dust off. But even that's not always needed if it's a fresh surface. Second, it's fast. Direct analysis of solid stuff. Right there.
You mentioned portability, too.
Yep. It's non-contact, barely damages the sample. We call it marginally destructive. And the instruments can be handheld. Robust. You can take it out into the field. You can even do analysis from several meters away, remotely.
Wow. And the light elements.
That's a huge one. LIBS is equally sensitive to light elements like lithium and heavy ones. That's pretty unique for atomic spectroscopy. Makes it incredibly valuable for things like battery materials.
Any other advantages?
Well, it's greener, you could say. Lower in environmental footprint, less chemical waste compared to traditional wet chemistry methods. And finally, you get this broad spectrum, usually 200 to 900 nanometers. It captures signals from almost everything at once. It's like getting a complete geochemical fingerprint of the sample in one go. Okay,
a complete fingerprint, minimal prep, sensitive to light elements. So what does this mean on the ground for actually finding and understanding mineral deposits?
It's transformative for exploration and mining geology, figuring out the modal mineralogy, basically, the exact percentages of different minerals.
Right, yeah.
In drill cores is absolutely critical. It tells you about the geology, where the valuable metals are concentrated. Really lets you do this quantification directly on the cores. You skip all those laborious selection and prep stages we talked about.
Can you give some examples? What kind of minerals are we talking about?
Sure. It can easily quantify common ore minerals like molybdenite or pyrite, and also the waste rock, the gangue minerals, quartz, various silicates, micas, things like that. It can even map out precious metals, gold, for example. You can see how it's distributed. Even on a millimeter scale, sometimes you find these tiny hotspots with really high concentrations, thousands of parts per million that you'd miss otherwise.
And those tricky light elements, lithium, beryllium.
Absolutely. It can map those in rock samples, too. Studies have used it, for instance, on granite-like rocks. They found LIBS could show that most of the lithium was held in the biotite mica, while beryllium was mainly in the feldspar. That kind of detail is crucial.
So it tells you not just what's there, but which mineral holds the element you care about.
Exactly. Especially if you combine the mapping with good calibration, what we call matrix-matched calibration. It pins down where trace elements reside, and it can even give you an idea of grain size. That's usually the domain of those expensive SEM systems we mentioned.
Right, the ones costing hundreds per sample.
Yeah. LIBS offers a much more accessible way to get at least some grain size information.
So it seems like it's not just identifying what's there, but mapping where it is within the rock, the mineral context, even grain size, all pretty much directly on the core sample.
That's the power of it. It dramatically speeds things up. And importantly, the analysis and the data processing can be standardized, automated. This means it can directly support or even improve upon the conventional core logging that geologists do.
How so?
Well, visual logging relies heavily on the geologist's expertise, right? But it can be subjective. Affected by fatigue or maybe inexperience, LIGI provides an objective, consistent mineral description across the board. It sort of democratizes that detailed mineral identification.
Okay, that makes sense for finding new resources.
Yeah.
But you also mentioned recycling and sustainability. How does LIBS fit into the circular economy, especially with things like batteries?
Yeah, that's another huge area. Lithium, as we said, it's incredibly strategic, not just for batteries in your phone or car, but industrial uses, medicine, even potentially for future fusion reactors. Its importance is just massive.
So managing old batteries is key.
Essential. If we want a proper circular economy, we have to efficiently recover materials like lithium, cobalt, nickel, manganese from end-of-life products, turn waste back into a resource.
And LIBS helps how?
Well, think about what happens when you recycle lithium-ion batteries. They get shredded. You've removed the plastic, copper, aluminum, iron casings. What's left is this stuff called black mass. It's mostly graphite from the anode, mixed with the valuable cathode metals.
And lithium.
And lithium, yeah. Typically somewhere between, say, 2% and 6% lithium by weight in that black mass. LIBS is being used to analyze this black mass directly, to quickly figure out the concentration of lithium and other valuable elements.
But is this straightforward, analyzing that kind of mixture?
It has its challenges.
Yeah.
The LIBS spectra from black mass are complex. Thousands of data points for each measurement. Simple ways of correlating signal intensity to concentration, what we call univariate calibration, they often struggle.
Why is that?
Because the background material, the matrix, changes a lot. And at higher lithium concentrations, you get effects like self-absorption, where the light gets reabsorbed before the spectrometer sees it. It complicates the signal.
Okay, so if the raw data is complex, messy even, with these matrix effects and self-absorption, how do you actually pull out accurate numbers? This sounds like a job for some clever data analysis. Is that where AI comes in?
Exactly. This is where artificial neural networks, ANNs, become incredibly powerful. ANNs are a type of machine learning, a multivariate approach. They're actually quite good for LIBS, especially handheld instruments, because they don't need massive computing power once they're trained.
How do they work with the spectra?
They're brilliant at finding complex, nonlinear patterns in data. They learn the relationship between the input, like the intensities of light at many different wavelengths in the spectrum, and the output you want, like the concentration of lithium. There's a really neat concept that Alvarez and colleagues highlighted recently, mineralogical pattern.
Mineralogical pattern.
Yeah. Instead of looking at just one spectral line for one element, you look at combinations of signals from elements that typically occur together in a specific mineral. So you might combine signals for molybdenum and sulfur to create a specific molybdenite pattern, or iron and sulfur for a pyrite pattern.
Ah, using the known chemistry of the minerals.
Precisely. These patterns, these combinations of signals, are then fed into the ANN. It's trained using known samples. This is called supervised learning. The ANN learns to recognize these patterns and associate them with specific minerals and their quantities. It's a novel way to use the spectral data.
Then does it work well?
Amazingly well. The studies show really high performance sensitivity, precision, accuracy, often up towards 99.9% for classifying minerals this way. It means the models are statistically solid and really effective. Plus, the ANN approach helps remove subjectivity. It can distinguish minerals even if they have quite similar overall chemistry based on these subtle spectral patterns.
So the AI helps sort through the complexity.
Right. Now, training the ANN takes time. You do that in the lab with good reference samples. But once it's trained, the network is robust. You can apply it to new, unknown samples out in the field and get results almost instantly. The calculation on the instrument itself is minimal because all the complex learning, the coefficient setting, was done beforehand. It's like preloading the intelligence.
That's pretty impressive. Near real-time, AI-powered mineral identification in the field or recycling plant. But, like any technology, it can't be perfect, right? What are the current hurdles or limitations? Where's the room for growth?
You're right, there are always nuances. One challenge is what happens at the laser spot itself. It's possible, especially with fine-grained rocks, that a single laser shot might hit more than one mineral phase at the same time.
Ah, so you get a mixed signal.
Exactly. That could potentially lead to, say, overestimating the most common mineral in that spot and underestimating the less common ones. However, the fact that the Libzan methods use the whole spectrum, relying on those multivariate patterns, helps to smooth this out somewhat. It compensates better than just looking at single element lines. And researchers are always working on improving laser focus and data processing to deal with this.
Okay, what else?
Another point is the quantification units. LIDAS naturally gives results in terms of area percentage on the surface you analyzed. But the mining industry usually thinks in weight percent. That's how they calculate metal grade and reserves.
So there's a conversion step needed.
Yes. Ideally, you need to know the volume of material that was ablated by the laser pulse to accurately convert area percent to weight percent. This is needed for direct comparison with results from reference methods like QueemScan, which provide weight percent but are much slower and sample destructive. Bridging that units gap is an active research area.
But even with those points, the advantages seem significant.
Oh, absolutely.
Yeah.
Despite those challenges, LIBS's ability to analyze directly on cores, its speed, its spatial resolution, which is actually often better for seeing overall texture than the ultrafine resolution of something like QueemScan. These are massive benefits. It still provides a much more objective and often more representative mineral description than relying solely on visual logging.
So what's needed to keep pushing this forward?
Really, the key is data. We need to keep building extensive, high-quality spectral libraries for minerals. The more good data we feed into these advanced mathematical approaches, like the ANNs, the better they become. The more reliable and versatile LIBS will be across all geological applications.
So wrapping this up, LIBS is clearly more than just a lab curiosity. It feels genuinely transformative, from speeding up how we explore for minerals deep underground, changing the way we map resources, to making the recycling of critical materials, like in batteries, much more efficient. It's really impacting resource management. So here's a thought to leave you with. As we look ahead, grappling with sourcing the materials we need and reusing what we have, just think about this tiny flash of laser light, analyzing microscopic spots. It might just be the key to unlocking immense hidden value, not just in rocks miles down, but maybe even in that old phone battery in your drawer. It's paving the way for a smarter, more sustainable, and better informed world for you.